Lews dot diagrams, and how do we make them? That's what you're going to find out today. By the end of this video, you should be able to make a Lews dot diagram for any atom on the periodic table. After this lesson, you'll learn how to connect those atoms to make bonds. Timeline for today is first we need to review valence electrons and what they are in order to make a Lews dot diagram. Then we're going to jump right in and figure out how to make these Lews dot diagrams. For future notice, I will be transitioning these timeline of the lesson down into the comments below. So if you're an educator out there and you want to know what the timeline is, you want to know what the Bloom's taxonomy is for each lesson, please check out the comments below. That's where I will be posting them from now on. Given what you already know about the periodic table from the previous lessons from me that of course you watched, what the heck do these random dots around these atoms mean? What would be your best guess as to what these dots would symbolize? Spoiler alert, I'm going to tell you what the dots mean, so if you don't want to know what they mean yet, pause the video now. Okay, let's jump right into what the heck these dots mean and how they apply to Lews dot diagrams. These dots are valence electrons. So if you didn't watch my previous video on the periodic table and what those valence electrons are, simply put, valence electrons are the electrons that are in the outermost, farthest away from the nucleus shell possible. So if you have an atom, they're the electrons that are all the way on the outskirts away from the nucleus. Those are considered your valence electrons. Those are the electrons that are available for bonding. A little shortcut to figure out how many valence electrons each atom will possess is by looking at this lovely little periodic table that I have up there, and that'll tell you in each group, so that's going down, up and down, each column, how many valence electrons should surround that atom in the outermost shell in each respective column. So for example, hydrogen is that tippy top one with 1 in it, and that means it has 1 valence electron around it. Whereas helium is all the way on the right side with the 2 on the top. That means it has 2 valence electrons, or 2 electrons in the outermost shell. So any of those positions in the column represent an atom specifically in its position and how many valence electrons it'll have in the outermost shell. As a quick reminder here, valence electrons are in the highest energy level, or the outermost shell. They are all the way on the farthest exterior of the atom. If you didn't want to use my handy little shortcut of a periodic table, there are 3 other ways to determine valence. The first is a shell model. So basically just draw a shell model. If you don't know how to draw a shell model, watch my previous videos, I tell you how to. The second way is to write out an electron configuration. And you would take into account all of the highest energy level electrons. So you'd look at the highest energy ones, whatever that number is the greatest, and those are the electrons you would count towards your valence electrons. If you don't know how to write an electron configuration, watch my previous video, I show you how to. And last but not least, there's orbital diagrams as a third way to determine what valence an atom will have. Those orbital diagrams, you're going to look at the highest energy level electrons, just like you did for electron configurations. And again, if you don't know how to make orbital diagrams, watch my previous video, I tell you how to. All of those videos are linked for your convenience in the comments below so that you can learn also how to make a shell model, electron configuration, and orbital diagram. Thank you and good night. Ah yes, the Lews dot diagram, made by Lewis, named after Lewis. And that's the picture that you see there. That is Lewis. Lews dot diagrams made by yours truly, Lewis. He's the guy that figured out you can take an element symbol, or an atom, and surround it with only the valence electrons via dots. That's what those dots were to begin with. And then use this to figure out how an atom will bond to another atom. The way you go about doing this is very similar to the shell model where you play ring around the rosy, pockets full of posy. In other words, you're filling up the dots, the valence electrons, around an element symbol up to 4 first. Then you go back and you pair them up together if there's more than 4. So after playing ring around the rosy, if you still have more than 4, that's the point at which you would go back and pair any of the lonely dots or the lonely electrons together. Now the reason you do this is because in an orbital diagram, only 2 electrons can fit in each box. Again, if you have no idea what I'm talking about with the orbital diagrams, please click on that link in the comments below and educate yourself. And due to the octet rule, we can only have 8 electrons around each atom accordingly. So before I show you how to actually do this, let's all have a baseline of steps of what to do when we get to this point. Step 1, if you wanted to draw the Lews Dot diagram for, say, oxygen, for example, we would write the element symbol first. We would write an O on our paper. No matter where you put it, just put an O on your paper. Write an O. Step 1, you put the element symbol, which is O for oxygen. Step 2, find the valence number of oxygen. So we need the valence electrons, not the total number of electrons. Make sure you keep those two separated in your head. We need the valence electrons. We need the number of electrons that are in the outermost shell of oxygen. And now we see that oxygen is number 8 on the periodic table. There are 2 electrons in the inner shell. Then there can be up to 8 electrons in the outer shell. Since there are 8 total, that means there can only be 6 in the outermost shell of oxygen. So oxygen's valence obviously needs to be 6, not 8. 8 is the total number of electrons. 6 is the number of electrons that are in the outermost shell, the valence electrons. Step 3. We now need to play ring around the atom, before pairing up electrons. So we go around first, 1, 2, 3, 4, then we go back for 5, 6 to pair up any lonely ones until we get to our total number of valence electrons. Let's go ahead and take a stab at it and try drawing the Lews Dot diagrams for phosphorus, bromine, silicon, fluorine, nitrogen, and hydrogen. Let's start with phosphorus. The first thing we have to do is figure out what phosphorus valence electrons are. So find phosphorus on your periodic table or use the little cheat sheet periodic table I had before. Phosphorus is right here. It's number 15 on our periodic table. Since phosphorus is 15, it has 15 total electrons, but not all of those are valence electrons. We need to figure out how many of those are in the outermost shell. With a valence of 15, and according to the shell model, we know that there can be 2 electrons in the innermost shell, and a max of 8 can fit in the next. So we have 8 in the next one. So that gives us a total of 10 thus far. We still have 15. So we have 1, 2, 3, 4, 5. So we have 5 electrons in the outermost shell of phosphorus. You could also just go back and look at my little cheat sheet valence electron periodic table and notice that it says 5. See, if you just look at the shortcut and you notice where phosphorus is on the periodic table, it says 5. So what do we do with those 5 valence electrons now? We need to play ring around the atom. So we have our P already written. I'm just going to draw it bigger right here. So there's our P, our phosphorus, and we need to put 5 valence electrons around it. We're going to go 1, 2, 3, 4. Notice I'm playing ring around the atom. I'm not pairing them up first. I go back and then pair them up. So 1, 2, 3, 4, 5. Now I've paired up 2 electrons, and there can only be 2 dots next to each other because of how we fill in our orbital filling diagram, where there's only 2 electrons opposite spins next to each other. You can't have more than 2 electrons right next to each other. So this would be our Lews Dot diagram for phosphorus. Yay, yes! Bromine is next to be scrutinized. Step 1, draw bromine's symbol, Br. That's the atomic symbol. Now we need to figure out how many valence electrons Br has. Well, bromine is all the way over here, and it has an atomic number of 35, but its valence electrons are not 35. That's the total number. So its valence electrons, let's check back at our little nifty cheat sheet, and we see bromine was in this column right here. So that means that bromine has 7 valence electrons. So let's play ring around the atom. 1, 2, 3, 4, 5, 6, 7. Woohoo! Notice I went around first where all of the electrons were by themselves, the lonely electrons, and then I went back and paired them together. Again, only in 2s, can't have more than 2. 3's a crap. Next, we're moving on to silicon. If we look back at our periodic table and we use our little shortcut of counting over columns, 1, 2, skip the transition metals, 3, 4, you'll notice that silicon is in that 4th column, therefore it has 4 valence electrons. Let's start by drawing silicon, Si, our symbol, and then we're going to surround silicon with its valence number of electrons, which we decided was 4 from the periodic table. We'll play ring around the atom, 1, 2, 3, 4. And that's all we have to do for silicon. Fluorine is the most electronegative atom on the periodic table. It's in the halogen column right before the noble gases. that means that it has 7 valence electrons, using our shortcut of counting across. Or you could also draw the shell model for fluorine, you could write out the orbital diagram, or you could do an electron configuration to determine the same thing. First, we'll draw fluorine's symbol, which is F, and we'll surround it with its valence number, which is 7. Playing ring around the atom, we have 1, 2, 3, 4. Now I go back in pair, 5, 6, 7. So in fluorine's case, we have these paired electrons, call those lone pairs, and we leave them alone because they already have a buddy. We do see that fluorine has 1 lonely electron there. And this knowledge comes in handy when we're trying to connect atoms together and make bonds, which you'll learn about in a later lesson. Next we have nitrogen, and nitrogen is in between carbon and oxygen. If we use our little shortcut and count over 1 column, 2 columns, skip the transition metals, 3, 4, 5, we'll see that nitrogen is in the 5th column and every element below it also has 5 valence electrons. So we're going to draw an N for nitrogen. And we know that nitrogen should be surrounded by 5 valence electrons. So let's play ring around the atom. 1, 2, 3, 4, and 5. Just as we talked about with fluorine before, we have a lone pair that we're going to leave alone, and we have 3 lonely electrons that are available for bonding, which we'll learn about in a later lesson. Last but not least, we have hydrogen, our good old friend hydrogen. Hydrogen is number 1 on the periodic table, meaning it only has 1 electron, therefore its valence also has to be 1. We're going to write an H for hydrogen and then put 1 little electron next to it for its valence electron. Try drawing some Lews Dot diagrams for any of the atoms on the periodic table that your heart so desires to make sure that you understand how to draw them. This comes in handy if you're able to draw them quickly and learning how to bond them later with single, double, and triple bonds. I hope this was helpful for you. It'd be pretty ducked up if you left this video without hitting that thumbs up button. Be sure to subscribe to my channel if you haven't already. Keep it quacky.
No ducks, no glory.